Hello everyone, Steve here with my newest and most dynamic clocks to date. There's two different sizes, a medium size and a large size. I call these crazy gear desk clocks. They have a lot of dynamic motion, they're super accurate. And we turn one of these around. The entire row of gears on the back side is continuously in motion. They look great, nearly silent, and best of all, they've got an accuracy of about 1 second per month. These designs are for sale on my mini factory. In this video, I'm going to describe the clocks, go over the evolution of the design, and basically how the design went from this to this. And then I will describe the controller that's inside the base that keeps these clocks accurate, and then also go over a few of the assembly steps to make it easier for you to build your own. Let's get into the introduction and show how these clocks work. This design started 4 or 5 years ago with a very small design. I like the symmetry of the design with 6 gears spaced symmetrically around the dial. The control circuitry was just a stepper motor with an AC transformer, and the AC powered one coil of the stepper motor, and then a capacitor delayed the signal to the second coil. Makes a great synchronous motor with one problem. You can probably hear it. It's really loud. This design ended up just getting shelved while I went in search of a better, quieter driver circuit. The first thing I tried when I was looking for a better driver circuit was a stepper motor controller called the A4988. It's real common. It's used in a lot of older 3D printers, really cheap. I never could get that thing to run very quietly. It was a little quieter than this design, but actually not a whole lot. And it had a few other things that would make this a bad clock driver. For one, it needed at least 8 volts. And then so now we'd have to be in search of a power supply of 8 volts. So then I kind of set the design for a desk clock on the shelf and let it sit and think about it. Eventually, I came up with a binary weighted resistor driver that's driven by an Arduino Nano, and it drives a 34 ohm stepper motor, not a real common stepper motor, but this motor uses very little current, and it's able to drive straight from the resistors out of the Arduino Nano. This design worked good enough that I could release what I called the silent desk clock. This was released as SP6, and it's relatively quiet. I actually designed that clock this size and in a somewhat larger format, but could never get the larger format to be quiet enough. It seemed to work sufficient in the small size, but the larger size just had a little bit too much gear noise. So it was initially released just as a small size using the Arduino Nano and resistor-based controller. A breakthrough came a year or two after that when I saw a circuit called a CNC Shield V4, which is it's a small circuit board that has 3 sockets for A4988 drivers, but instead of plugging in an A4988, I plugged in a TMC 2208, cannibalized one of the other ports, and plugged in a real time clock. It has an Arduino Nano. All these coupled together made this a really quiet controller. The TMC 2208 is the secret. It is smooth and quiet. There's a few hardwired connections on the back side of the board that are required in order to make this work. The algorithm that's programmed into the Arduino Nano uses jumper wires that you can add or remove the jumper wires and change the speed without having to reprogram the Arduino Nano. With the CNC Shield V4 driver circuit, I was able to release another clock, the larger size, with the CNC Shield V4. It made this clock really super quiet and allow, where I felt comfortable releasing that. So then the next step in the evolution of this design is, so I designed a custom board taking all the features used in the CNC Shield V4 and bringing them into a smaller package. It still uses the Arduino Nano, the TMC 2208. As soon as I released this clock as the large silent desk clock, I really liked it a lot at the time. I liked the easy to read dial, but I thought that the gears were a little bit hard to see from a distance. They just looked like circles. And I kept looking at this other clock that I have in my office. It's just a commercial clock that has a lot of continuous motion. And I liked that style, and I thought, I want to design a clock even better than this one. And I wanted to have some continuous gear motion. That was the next step in the journey to designing these clocks. I decided to go back to an involute style gear tooth profile and merge the spoke and the gear teeth into one. Prints really cleanly, and I decided to add all the extra motion. 5 of these 6 gears on the back row are just dynamic motion. They don't actually do anything related to keeping time. Only the first gear, driven by the motor here, actually drives the second hand. The rest of these are all just motion, it gives it a great look. And then there's even 2 gears up front that are extra dynamic motion. It looks nice when you're changing the time. There's a little friction clutch right here, so I can change the time without pushing the hands, because the second hand would get in the way. So it looks great also when you're changing the time. So that's kind of a summary of how this design evolved from this into this. And lots of changes along the way, but I really like it. I hope you do too. The frame on these clocks is a segmented design that needs to be combined together into a solid unit. And that is done with a couple of music wire rods, and there's holes drilled in the legs and in the back piece that will put these pieces together. These holes for the rods are expected to be tight. You may need to drill them out so that the rod will go in. And you really just start on these by putting the shafts into position, and you can't necessarily just push it together, but by wiggling side to side, it will often just push into place. And then add a wood screw to hold it in place. And then check the alignment that it's relatively straight. When you set it on a flat surface, you want that to be as straight as possible. We can now start adding the gears into the clock. A couple of things that really help is the pages in the manual showing where each of the gears is going to fit relative to the frame. This is actually the back frame for the medium-sized clock. The manual shows the large clock. It's identical other than these small little fingers that stick out on the large clock that don't exist on the small clock. Other than that, the assembly is identical. And what really helps is the diagrams that show the gears in the actual positions. This diagram shows the labeling of the gears 0, 1, 2, 3, 4, 5, 6, 7, and 8, with a B in the name indicating that it's a back row gear, and without the B is one of the forward gears. And then on the next couple of pages, it shows them in the approximate locations that they exist here. So gear 4B is in the upper left corner, gear 5B is in the upper right corner, and then the next page shows the remaining gears, which are the upper layers in the clock. So we're going to want to start by placing the back row gears and trying to line up all the printed gears with this picture, and then we can place them into the clock. So there's a whole bunch of gears in this clock. That's part of what gives this clock so much dynamic motion. And what I want to start with is just lining up the gears with the diagram, and then I'll place them into the frame. This one with a 25 teeth, 10 on the pinion, that looks like this one, gear 0B, 25, 10. Here's one we'll get to later. It's got 32 teeth on the outer row. I'll set that aside. I've got two 15 tooth gears. There's a tall one and one that's not quite so tall. Here's two gears with 25 and 15 teeth. There's one that's a tall pinion and one with a pinion that's not quite so tall. And then gear 5B, 2510. I'm just going to set them here and then start placing them into the clock. So I am now going to move these gears to their approximate location. I'll set gear 2 off to the side. And then I'm going to go forward in the manual to the page. This is the critical step. This is the page showing the alignment of the gears in the back row on the left side. If we start by placing arbors into the holes, and I've drilled some of these holes out so that the arbors are a little bit loose but not sloppy. And what we want to start with is adding the two gears in the upper and lower positions. And then we need to line up the spokes into a near straight line. It's not a perfect straight line. At that point, we can add the center pinion and get these gears to mesh and make sure that the spokes are in a near straight line. If you don't do that, the gears will bind. The next page shows the gears on the right-hand side, and this is the gear 5 arbor, and I only partially assembled it, 1.65 inches extended out from the shaft collar. It's just easier to assemble without the rest of the gear in the way right now. So this will stick through to the bottom because this arbor will have a knob on the back for setting the time. So I'm gonna go ahead and add that right now. This is just to help protect the table a little bit. And you can do this assembly on top of an empty spool holder, or I'm just going to prop the clock up on the hold down that gets used inside the base later. So when I'm adding the 3 gears on the right, they're going to mesh no matter how you put them in. There's no real critical alignment on this side because they all just mesh around their perimeter. So I can test that these spin, and they spin easily. So now we can just continue through the manual in the order that they show. This is the gear 2 assembly, and it drops into the center arbor. It drops into the central arbor position, and it's going to mesh with gear 1, and I can still see that everything spins smoothly with no binding. Now I'm going to go back a couple of pages and find this diagram to line up all the remaining gears and figure out which one goes where. The easiest one is gear 5. Just because there's no pinion on that one. Then the 32 tooth gears, those are the ones with 3 rows. This center row is really just cosmetic, but it does help identify which gear goes where. I'm going to place the one with the tall shaft over in their ultimate position. I'm going to move gear 5 over by gear 5. Let's see what else we have. I have gear 6, and I can tell that's this one, that the hand will be added to that one. In gear 8, we'll have a hand added. There's a little step when the hand gets added. And I just want to test that those spin freely. We'll get to those later. I've got 2 small gears left. One with a tall pinion, that's going to go here. One without a center pinion, that's gear 1. And then gear 4, 30, 10. That one is going to go here. So now going back into the manual, I've added gear 2 to the central arbor, and then gear 3, 32, 20. That adds in and meshes with gear 2. Gear 4 meshes with gear 3. And now we need to add gear 5. And because I took this clock apart, now I need to put the gear 5 arbor back together. That starts with the pen spring, gear 5 at 30, and then gear 5, 15. And I'm compressing the pen spring as I put this together right now. And what I'm looking for is that the gear 5, 15. What I'm looking for is that the arbor extends towards the front, the same amount that the other gears have extension. So about 3/10 of an inch. So that's what I see right here. That's going to be the proper positioning and compression of the pen spring. So I've already done the step where I've added the knob to the back. Then I need to add gear 1 and gear 0, and these are going to go down at the bottom. They don't mesh with anything just yet, but it's easier to add them now. Gear 6 gets added to the central arbor, and that one meshes with two gears, a gear 5 and a gear 1. And then I can add gear 7. The next page shows the last remaining gear, which is gear 8. And now we can add the dial. And these clocks there's a lot of arbors that need to line up with holes in the frame, but it's actually relatively easy because they're all somewhat exposed, other than the two at the very back. But just one by one, wiggle the arbors, and then the frame just dropped down. Everything is lined up, and I'm ready to put the base on it. So the first test, I'm running the electronics outside of the base. That makes it easier to debug all the electronics and the jumpers and the cabling, and then I'll put everything into the base later. But this step is relatively simple. I like to put it together while the clock is still lying on its back. That way the gears don't go out of alignment. You don't necessarily have to attach the bottom screws just yet, because you will have to take the clock apart to add the electronics back into the base. But it's relatively easy, so I'm just going to add 2 screws to hold the frame in position. And everything is working properly. I can change the speed. If I had tested this, if I had the cable plugged in backwards, the second hand would run backwards. The clock would still run, but you just wouldn't be able to tell the time. I don't have this set at the right speed yet, so that's why we would be adjusting the jumpers. And so I'm going to reverse the cable. I'll show what it looks like if you have cable in the wrong position. This is a stepper motor that needed a crossover cable. The motor is just jittering back and forth. I can still tell that there's power applied to it, but it's not rotating. So unplug power, and I'm going to switch from the straight position to the crossover position on the Silent Shield clock controller. And when I put it back in, then it's running. When I apply power, the clock is running properly. So before we go too much farther, I'm going to run a few tests. I'm going to start with the jumper in the position to enable debug testing, and then one by one I can see this is just a simple that I can see the LED light up when I put the jumper in each of the 3 positions. The other debug modes to test are just an LED blink test. The power LED is on, but the second LED is blinking at 1 hertz. That's a half second on, half second off. That's just a simple test to tell that the Arduino is programmed. The next test, 1101, is a real-time clock test. This is going to blink at a half a hertz. That means 1 second on, 1 second off. Every time the real-time clock advances by 1 second, the LED will toggle. So a half hertz blink rate. The next test is a stepper motor test, 1110, and this isn't the proper rate for this clock, but the stepper motor is running in one direction at, let's just call it a medium speed, and by adding the last jumper, 1111, the stepper motor reverses direction and it's going at twice the speed. So now we can go to the exact speed that's needed for this clock. So if we look at the table for the jumpers, it shows this is SP10, the medium-sized clock, and I happen to have it with 400 step motors. So I want 0010. So that's ignoring the first position, 0010. The clock is running properly in the correct direction. Now what I want to do is put the electronics into the base, keeping in mind the direction of the cable so that I plug it in the same direction when it's all assembled. And I will be putting this controller into the retainer. Oops. When this goes into the clock, the custom controller versus the CNC Shield V4 controller are physically the same size once the retainer has been added. So the clock will run identically with either version of the controllers.